You know, when you think of a coastline, you probably picture a fixed line on a map, right? The place where the land just stops. But the truth is, it's one of the most dynamic and ever-changing places on Earth. Today, we're diving into the incredible forces that are constantly reshaping our world's shorelines.
Just look at this amazing view of the U.S. East Coast. You can see all those familiar shapes. Cape Cod, Long Island, the Outer Banks. They look so solid, so permanent, don't they? But what you're really looking at is a battlefield. It's a non-stop war zone between the land and the massive power of the ocean. So what are the forces actually slugging it out here?
So to really get a grip on this, we have to stop thinking of the coast as a simple line. It's a boundary, sure, but it's a boundary that's always in motion. It's a zone where land and water are constantly meeting, clashing, and literally reshaping each other.
And here's the bottom line. The shape of every single beach, every cliff, every bay that you've ever seen is the result of a relentless tug-of-war. And who are the main players in this fight? Well, you've got the incredible energy of the waves, the constant push of the wind, and maybe the most important factor of all, the water level itself, which can swing from simple tides to catastrophic storm surges.
All right, let's start with the most obvious and, frankly, the most powerful agent of change, waves. These things are the master sculptors of our shorelines. They are basically delivery systems, transporting enormous amounts of energy from the wide-open ocean right to the coast doorstep. So how does a wave even work? Well, it all starts with wind. Tiny molecules in the air bump into the water's surface, transferring a little bit of energy. As the wind keeps blowing, more and more energy gets added, and the wave gets bigger and bigger until it's just too steep to support itself. Then, as it gets close to shore, the bottom of the wave starts to drag on the seafloor, slowing down. But the top of the wave is still moving fast, so it basically trips over itself and collapses in that beautiful crashing break we all know and love.
Okay, here's something I bet you've noticed at the beach. You can look way out and see waves coming in at a clear angle, but by the time they actually wash up on the sand, they almost always seem to be perfectly parallel with the shore. What is going on there? It's not a coincidence.
The answer is a really cool bit of physics called wave refraction. Imagine a wave coming in at an angle. The part of the wave that hits the shallow water first starts to drag on the bottom, and it slows way down. But the other part of the wave, still out in deeper water, is cruising along at its original speed. This speed difference forces the whole wave to pivot, or bend, until it lines up with the shoreline. It's amazing.
And here's the crucial consequence of all that bending. Wave refraction acts like a giant magnifying glass, focusing all of that raw ocean energy directly onto any piece of land that sticks out, like a headland or a promontory. This is exactly why you see those dramatic steep cliffs in those areas. They are taking a concentrated beating from the waves, which just massively speeds up erosion.
Now, understanding these forces isn't just a cool science lesson. It's absolutely critical for predicting risk, especially when a big storm is on the way. So how do scientists take this knowledge and use it to figure out just how bad a storm is going to be for a particular coast?
I mean, this is the million-dollar question for anyone who lives near the ocean, right? When a hurricane is churning offshore, how do scientists make the call between, we might lose a little sand, and this is going to be a landscape-altering, catastrophic event?
Well, the answer is surprisingly straightforward. It all boils down to a simple, direct comparison. Scientists look at just two key things: the predicted height of the water, that's the storm surge plus the waves on top, and the height and shape of the land, specifically those coastal dunes that act as our natural line of defense.
And this table perfectly illustrates the playbook they use. They have a scale with 4 distinct levels, or regimes, of coastal impact. Each one describes a different scenario based purely on how high the water gets compared to the dunes. You've got swash, collision, overwash, and inundation. Let's break them down one by one.
First up is the swash regime. Think of this as your normal, calm day at the beach. The water washes up on the sand, that's the swash, but it never even touches the base of the dunes. In this state, the dunes are perfectly safe and any coastal property behind them is fine.
Next, things start to get a lot more serious. This is the collision regime. Now, the water level is high enough that waves are smashing directly into the face of the dunes. They act like a battering ram, chewing away at the sand and carving out a steep little cliff, which scientists call a scarp. This is when you start to see real damage, like beach boardwalks getting destroyed.
The third level, overwash, is a major escalation. Here, the waves are so high, they don't just hit the dune, they go right over the top of it, carrying tons and tons of sand from the beach and dumping it inland. This is what buries coastal roads and floods the ground floors of homes. The primary barrier has been officially breached.
And finally, we have the most destructive, worst-case scenario, inundation. In this regime, the storm surge is so high that it completely submerges the dunes. They offer zero protection. It's as if they're not even there. The ocean just pours inland, causing the kind of widespread, catastrophic flooding we see in the most powerful hurricanes.
Now, all these storm impacts are incredibly dramatic, but they happen on a human timescale, days, hours. So let's zoom out, way out, and look at the much slower but even more powerful geological forces that shape our coasts over thousands and millions of years.
On this massive geological scale, coastlines are really defined by one big question. Is the sea level rising or falling compared to the land? And that gives us two basic types of coasts. You have submergent coasts, which you get when the sea rises or the land sinks. And you have emergent coasts, which happen when the sea falls or the land itself gets pushed up. If you look at the east coast of the United States, that is a textbook example of a submergent coastline. When the sea level rose after the last ice age, the ocean just backed up into old river valleys, creating these huge sprawling estuaries like the Chesapeake Bay. In other places, it flooded valleys carved by glaciers, forming those incredible fjords. And those famous barrier islands, like the Outer Banks, they might just be old sand dunes that got stranded as the sea rose around them.
On the flip side, an emergent coast gives you all these fascinating clues of a past when the sea level was much higher. You can find things like old wave-cut cliffs and flat platforms that are now sitting high and dry, way above the current shoreline. You might even find ancient coral reefs left stranded on dry land. It's like a geological ghost story.
So what's causing these massive long-term changes in the first place? Well, the single biggest driver, by far, is the amount of water that's locked up in glaciers and ice sheets. But ocean temperature is also a huge factor. As water gets warmer, it physically expands. And then you have these deep geological forces, like the speed of seafloor spreading, or the land slowly bouncing back after the weight of glaciers is gone, that can change the shape of the entire ocean basin.
So, as we've seen, our coastlines have never, ever been static. They're the product of this ancient, ongoing dance between the land and the sea. But here's the critical thing for us today. The pace of that change is speeding up. Understanding all of these forces, from a single wave breaking on the beach to the melting of ancient ice sheets, is really the first step. But the real question is, are we ready for what's coming next?